Quoting Neil deGrasse Tyson. On Friday, April 13th, 2029, an asteroid large enough to fill an entire football stadium will pass so close to Earth that it will fall below the height of our communications satellites. We didn't call this asteroid Bambi. Instead, he was called Apophis, the Egyptian god of darkness and death. If Apophis's trajectory remains as it is now, Earth's gravitational pull will send it on a trajectory that will cause it to collide directly with Earth in 7 years, 2036, on its next orbit. In this case, Apophis would hit the Pacific Ocean between California and Hawaii, and a tsunami would sweep the entire west coast of North America, burying Hawaii and destroying all the land masses of the Pacific Rim. Neil Douglas Tyson welcomes us with perspective. Apophis is undoubtedly one of the most dangerous asteroids of our time, and in 2029, it will pass so close to Earth that it will be closer to Earth than our moons. The big question then is what effect this flyby will have on the asteroid. Perhaps in 2029, Apophis will be pulled into orbit, putting it on a direct collision course with Earth. If he misses the key, he will be so distracted that we have nothing to fear in 2036. It looks like luck, and we have to ask ourselves if we can leave the fate of civilization to luck. Apophis is a small asteroid. At 340 meters in diameter, it is much smaller than the large asteroid that wiped out the dinosaurs 66 million years ago. Asteroid Chicxulub, which hit the sea off the coast of Mexico, had a diameter of 15 kilometers. Nevertheless, Apophis's greatness is enough to cause terrible chaos and destruction on Earth. Neil deGrasse Tyson said Apophis could trigger a tsunami that could destroy nearby coastlines and wash away islands. When Apophis makes a safe and distant flyby of Earth on March 5, 2021, astronomers will take advantage of this unique opportunity to once again accurately determine the asteroid's orbit around the Sun. Astronomers have since gone ahead and ruled out a collision within the next 100 years. Nevertheless, some experts are cautious on this matter, saying that we should wait until 2029, when Apophis will approach the Earth again, and only then we can make real assumptions about the future and the risk of any collision. Simply put, this Apophis threat continues to exist and cannot be underestimated. We don't know exactly what will happen until 2029. Astronomers base their predictions on observations with optical telescopes and ground-based radar to determine the orbit of each near-Earth object as accurately as possible. But asteroids are complicated. They are rarely seen, and their size makes them very difficult to observe. NASA astronomers observe the heavens as closely as possible, and then report their estimates to NASA's Planetary Defense Coordination Office. If there is a threat of a collision, the agency will issue a planetary asteroid warning. But NASA is optimistic. The representative emphasized that Apophis's orbit can be determined very well as early as 2021. Scientists used this opportunity to obtain incredibly accurate information about Apophis's distance and orbit. NASA believes this research is promising and fully sufficient to prevent a global collision. Apophis could still hit Earth one day, so it's important to do better to study objects like this asteroid. Previous radar observations suggest that Apophis is bilobed or bean-shaped. Fireform is a relatively common form in near-Earth asteroids. Two lobes mean that the asteroid consists of two main parts joined by a narrow belt. This form is often formed when two small asteroids collide and blind each other, or when a larger asteroid is pulled apart by gravity or two impacts. The two-layer structure provides important information about the asteroid's composition, density, and internal structure. To better understand the dynamics and behavior of such things, we need to know more precisely. In addition to shape, an asteroid's rotation speed and the angle it rotates determine its future trajectory and response to contact with Earth's magnetic field. When Apophis enters the gravitational field of our planet in 2029, this orbital state will change, and contact may even cause an asteroid earthquake, resulting in strong seismic tremors on Apophis. Then changes in the asteroid determine the danger ahead. Apophis does not come alone. Then I breathed a sigh of relief and thought, thank God Apophis won't hit us in 2029. Well, there's something to cheer about, because Apophis isn't alone. We know of about 25,000 objects that could be on a collision course with Earth at any given time. Apophis is the most dangerous of these asteroids and is its big brother Bennu on this scale. Bennu is a near-Earth asteroid about 490 meters in diameter that also regularly passes by Earth. The probability of Bennu hitting Earth is also currently estimated to be low. That's a good thing, because the consequences of such an event would be dire. Although Bennu's orbit is currently harmless, it needs constant monitoring. In general, we know very little about asteroids and cannot rule out the possibility that this deadly projectile could suddenly change its orbit. This could happen, for example, if asteroids collided with each other. OSIRIS-REx and DART-FIGHT asteroids. It is truly fantastic to see what scientists from all over the world have come up with to protect our Earth and civilization from outer space. NASA designed the OSIRIS-REx and DART space missions to further our knowledge of asteroids. The OSIRIS-REx spacecraft was launched in September 2016 and visited asteroid Bennu. There, the probe briefly crashed into the asteroid's surface, stirred up material, collected a sample, and flew back to Earth. A link to steroids was created in October 2020. In 2023, samples landed in Texas, USA. The sample container contains a powdered black surface material, and several laboratories around the world analyzed the powder. Preliminary analysis results indicated an abundance of water and organic molecules, as well as unknown material requiring further analysis. Knowledge of this composition can provide us with valuable information in the event of an emergency. If an asteroid hits us, we have to fight it somehow. Whether we want to blow it up or push it away, knowing the exact composition and density of asteroids will be critical to success. The OSIRIS-REx zone remained in space, becoming the OSIRIS-APEX mission, and the next target for sampling was the monstrous Apophis. Another breakthrough in asteroid exploration was the DART spacecraft, which was designed exclusively to crash into the binary asteroid Dimorphos. NASA had planned for the asteroid's orbit to take about 72 seconds, but the collision shifted Dimorphos's orbit by 33 minutes. In an emergency, such a mission could save the planet. Japan lands on asteroid Ryugu. Almost no one knows that Japan has also studied the asteroid in detail. The Japanese Aerospace Exploration Agency, JAXA, launched its Hayabusa 2 mission on December 3, 2014. After nearly 4 years of travel, the probe actually reached the giant asteroid Ryugu in June 2018. Ryugu is a C-type asteroid, known for its rich composition of organic and hydrous minerals. Among these organic structures, asteroids and comets are still suspected to be the true harbingers of life in space. So our research is not just about protecting asteroids. These things may also give us answers to the question of where life originated on Earth. One of the main objectives of the Japanese mission was to make a detailed map of the Ryugu surface. Hayabusa 2 collected 2 samples and placed 3 rovers on the asteroid's surface. Since then, Mars meets Minerva 2.1a and Minerva 2.1b, as well as Ryugu, the mascot of the German land. Long-term observation will provide us with additional valuable information about the asteroid's physical and chemical properties. Hayabusa 2 left Ryugu in November 2019 and returned safely to Earth in December 2020 with collected samples. These samples were given to scientists all over the world. To the researchers' surprise, a total of 15 amino acids were isolated from the powder. As the building blocks of proteins, amino acids are the foundation of life. It's just a matter of time to make a connection. If you look at the history of asteroid and comet collisions with Earth, the perspective is really easy. Throughout Earth's history, major impacts occur every 100 million years. The last asteroid of this size was Chicxulub. Smaller asteroids and comets have hit Earth many times since then, but as the Chelyabinsk incident shows, these are enough to cause devastating destruction. In 2013, an undiscovered asteroid with a diameter of about 20 meters exploded in Chelyabinsk, Russia. It exploded 30 kilometers above Earth, but it released energy equivalent to 500 kilotons of TNT. Although not directly killed by the impact, the shockwave injured 1,500 people and damaged 7,200 buildings in 6 cities in the region. Most injuries are caused by curiosity. People saw a flash of light and rushed to the windows. The shockwave traveled at the speed of sound and shattered windows after the flash, leaving people with serious injuries. In 1908, a comet about 30 meters in diameter struck the Tunguska region of Russia. The comet didn't even reach Earth, but the explosion ripped apart an area of 2,150 square kilometers and uprooted nearly 80 million trees like matchsticks. Experts estimate that the force of this explosion was 1,000 times greater than that of the atomic bomb in Hiroshima. If it had happened above the city, it would have been completely destroyed. Both asteroids were relatively small, but still caused significant damage. Asteroids as small as a few kilometers across could threaten our entire civilization. The impact alone can destroy a continent. The tsunami and its consequences, climate change, can lead to famine and other global catastrophes. The next big thing is just a matter of time. Don't miss an upcoming top video and subscribe now. Black holes are among the most interesting and fascinating objects in the universe. At their core, black holes are regions of space where the gravity is so strong that nothing, not even light, can escape. It forms when a massive star runs out of nuclear fuel and collapses under its own weight. The simplest type is a stellar black hole formed from a single star. But supermassive black holes are much larger and are at the centers of many galaxies, including our own Milky Way. Supermassive black holes contain millions, sometimes billions, of times the mass of the Sun. Despite their size, these giants are shrouded in mystery. One of their main features is the event horizon, the boundaries of which nothing can return. At this point, the gravitational pull is so strong that the laws of physics begin to break down. In addition to being a one-way ticket, black holes have a profound effect on their surroundings, shaping the galaxy itself. Another aspect is how these supermassive black holes grow. They can gain mass using gas, dust, and even nearby stars. This accretion disk can cause rotating material to become a black hole, heating up and releasing energy due to friction. This process can create the brightest objects in the universe, known as quasars, which emit light at great distances. Their luminosity reveals not only the presence of black holes, but also their growth history and the evolution of their galaxies. Interestingly, the relationship between supermassive black holes and their galaxies is complex. Studies have shown that the mass of a supermassive black hole correlates with the mass of a galaxy, suggesting a correlation between their evolution. This interaction raises new questions about the life cycle of galaxies, challenging scientists to unravel the complexity of these cosmic giants. As we continue to explore, black holes not only expand our understanding of gravity and space, but also inspire awe at the grand architecture of the universe. Gamma-ray bursts are among the most powerful explosions in the universe, releasing as much energy as the sun emits in a matter of seconds. These cosmic events challenge our deep understanding of stellar processes. Traditionally, we've seen stars as relatively stable objects that go through predictable stages of life, going through the final stages, like a white dwarf, a neutron star, or a black hole. However, gamma-ray bursts occur under conditions we are only beginning to fully understand. Most gamma-ray bursts are thought to originate from massive stars that have run out of nuclear fuel and caused catastrophic disintegration. This collapse produces a black hole or neutron star, fused with jets of high-energy particles traveling at nearly the speed of light. The surprise is that these jets can penetrate the star's outer layers, producing bright bursts of gamma rays. The discovery suggests that the life cycles of stars are more complex than previously suspected and involve powerful energetic phenomena that could destroy what we know. In addition, the study of gamma-ray bursts extends beyond individual stars. They provide information about the conditions of the early universe. These explosions are often observed at great distances, suggesting that the universe was more dispersed during its formative years. Understanding their frequency and behavior can help astronomers piece together the history of star formation and evolution, giving us a more accurate picture of the universe. Gamma-ray bursts not only push the limits of stellar theory, but also act as cosmic beacons. They shed light on the processes that govern the life and death of stars, bridging our current knowledge of the mysteries hidden in the night sky. As we continue to study these phenomena, they promise to change our understanding of stellar physics and the grand story of the universe. Antimatter is a fascinating counterpart to the matter that makes up our everyday world. While matter is made up of protons, neutrons, and electrons, antimatter is made up of antiparticles. These antiparticles look like shadowy versions of their counterparts in matter with the same mass but opposite charge. For example, the antiparticle of an electron, called a positron, carries a positive charge instead of a negative one. When a matter particle comes into contact with its antimatter twin, they annihilate each other, releasing energy in the process. This characteristic makes antimatter a powerful source of energy, although it is not suitable for practical use. One of the great mysteries of antimatter is its rarity in the universe. According to the Big Bang theory, equal amounts of matter and antimatter should have been produced. However, our observable universe is dominated by matter, and only traces of antimatter have been detected. This disparity raises profound questions. Where did all the antimatter go? Some researchers suggest that subtle differences in the behavior of matter and antimatter may have played a role in this disappearance, hinting at a new physics that challenges our understanding of the new universe. Another interesting aspect is the potential applications of antimatter. Scientists predict that it could be used in everything from advanced propulsion systems in space travel to powerful medical monitoring techniques. For example, positron emission tomography, or PET scans, use small amounts of antimatter to create detailed images of processes in the human body. Although the production of antimatter is currently a costly and resource-intensive endeavor, the possibilities it offers inspire researchers. In addition, the study of antimatter not only reveals the mysteries of the origin and structure of the universe, but also reveals the undiscovered laws of physics. Researchers are investigating whether there is a way to produce or find antimatter, or what the consequences would be if we discovered regions of antimatter in space. As we delve deeper into space and the nature of reality, antimatter is a tantalizing frontier that invites us to explore the fundamental truths of the universe we inhabit. Magnetars are a unique breed of neutron stars characterized by extremely strong magnetic fields. Although all neutron stars originate from the remnants of supernova explosions, magnetars outgrow these remnants. The magnetic field of a typical neutron star is about 1 million times that of Earth. But magnets boast magnetic fields that are 1,000 times stronger than this, reaching 1 quadrillion Gauss. This great magnetic force leads to amazing habits and behaviors. One of the most fascinating properties of magnets is their ability to generate large amounts of energy. These explosions can be incredibly powerful, often equal to the energy released by the sun in years, all in a matter of seconds. When magnets undergo these violent outbursts, they can emit not only gamma rays but also X-rays, making them the brightest objects in the universe during these events. These energetic outbursts allow astronomers to study them even from a distance. In addition, magnetic stars exhibit an unusual phenomenon. As with seismic activity on Earth, strong magnetic stress in the magnetic crust can cause sudden changes, resulting in earthquakes that can release large amounts of energy. These stars can also produce subtler variations in brightness, complicating their appearance and behavior, adding difficulty and intrigue to scientists trying to study cosmic phenomena. Magnetars are exceptional interstellar objects with magnetic fields so strong that they defy our normal understanding of physics. Their energetic explosions, deep magnetic influences, and the dramatic starbursts they create tell us a lot about the basic workings of the universe. As researchers delve deeper into their mysteries, magnetars continue to enrich our understanding of the universe's exotic inhabitants. Fermi's paradox poses a question that has puzzled scientists and astronomers for decades. Named after physicist Enrico Fermi, he essentially asks, with billions of stars and potentially even more planets in our galaxy, where is everyone? Given the vastness of the universe and the existence of a habitable world, the paradox represents a fundamental contrast between high probability, extraterrestrial civilizations, and the lack of clear evidence for their existence. Several theories have emerged to explain this mystery. One explanation is the rare Earth hypothesis, which suggests that although simple life forms may be widespread throughout the universe, the specific conditions that give rise to complex civilizations are rare. Protective features such as a stable planet, a suitable atmosphere, a large moon, or a gas giant can limit the emergence of intelligent life. Hence, the Earth may be an anomaly, with a combination of conditions leading to advanced beings. Another interesting theory is the Great Filter, which may be some stage in the evolution of life that could be incredibly large. This filter can occur before or after the development of intelligent civilizations. If it was established earlier, it means that many species did not evolve beyond simple organisms. Instead, if it is located after that, it raises an even cooler prospect. Intelligent civilizations can often self-destruct through war, environmental catastrophe, or technological challenges, preventing them from reaching or eventually discovering each other. Finally, some have proposed the idea of the zoo hypothesis. This perspective suggests that advanced extraterrestrial civilizations are aware of humanity, but zookeepers seem to observe animals where they live. Perhaps they read us from afar, allowing us to grow naturally without interference. This raises interesting questions about the nature of intelligence and the ethical dilemmas of contact. Fermi's paradox remains more than just a scientific question, but an invitation to think about our place in space and the possibilities beyond our understanding. Cosmic rays are cosmic particles that come from space and continuously bombard the Earth. These particles include protons, electrons, and nuclei, some of which travel at nearly the speed of light. When scientists capture and study cosmic rays, they reveal valuable information about the universe and the processes that produce these high-energy phenomena. By analyzing the composition and energy of cosmic rays, researchers can trace their origin and better understand the environment that produces them. One of the main concepts of cosmic rays is their connection to supernovae, black holes, and neutron stars. These explosive events and dense interstellar debris act as powerful accelerators, pushing particles to extreme speeds. As cosmic rays pass through Earth's atmosphere, they collide with air molecules, producing secondary particles. By detecting these secondary particles with ground-based observatories, scientists are tracking the potential sources of cosmic rays and the potential for such massive energy production. In addition, the study of cosmic rays provides a window into the fundamental nature of matter and energy in the universe. When these rays interact with other cosmic rays or matter, they can create new particles, some of which may hint at phenomena outside the standard model of particle physics. For example, researchers have discovered that high-energy cosmic rays are associated with distant astrophysical events, revealing connections between our planet and the farthest reaches of the universe. In addition, cosmic rays can affect the Earth's atmosphere and climate. Their interaction can create clouds, which over time affect the weather. By examining these interactions, scientists understand the effects of cosmic forces on Earth conditions. The study of cosmic rays not only enriches our understanding of high-energy particles, but also reveals the relationship between cosmic events and our own planet. Dark matter is one of the universe's greatest mysteries. Although we can't see it, it makes up about 27% of the mass energy of the universe, and its existence is indicated by its gravitational influence on visible matter. For example, galaxies rotate at speeds that should tear them apart, but they hold together, providing an invisible gravitational pull. However, this shows a strange behavior that defies our understanding of cosmic structure. One interesting aspect of dark matter is its clustering. Observations show that dark matter tends to clump together, forming significant structures such as halos around galaxies. However, these halos often do not correspond to the observed distribution of matter. When studying galaxy clusters, researchers expected that the dynamics of visible galaxies would be altered by mixing with dark matter. Instead, dark matter dominates these large-scale structures, complicating our models of how galaxies and clusters interact in the cosmic landscape. Another peculiar behavior is a phenomenon known as dark matter interactions. Although dark matter is thought to interact primarily with gravity, some theoretical models suggest that it may have other, weaker interactions that have yet to be confirmed. Experiments looking for this interaction have been inconclusive, leaving scientists baffled. If dark matter has additional interactions beyond gravity, it could mean an overhaul of our understanding of fundamental physics, which applies to everything from particle physics to cosmology. This strange behavior suggests that our universe is more complex than we first thought. As researchers continue to collect more data and test new theories, efforts to uncover the nature of dark matter could not only increase our understanding of cosmic structure, but also lead to revolutionary discoveries about the fundamental workings of the universe. With every observation, we get closer to unlocking the mysteries of dark matter, and each discovery raises more questions, making the field of cosmology vibrant and fascinating. What mysteries lie beyond the observable universe? Our observable universe spans 93 billion light-years, but that's probably only a fraction of what it is. From multiple theories to potential changes in the laws of physics, we'll explore key ideas that challenge our understanding of reality. Join us as we push the limits of cosmic knowledge and wonder what might be beyond our cosmic horizon. The observable universe is defined as the part of the universe that we can see or see from Earth, extending from the beginning of space to the farthest distances that light can travel. Because of the finite speed of light, which travels at 300,000 kilometers per second, we can observe regions of space long enough for us since the Big Bang. Currently, this distance is about 13.8 billion light-years, meaning that we can detect objects up to 13.8 billion years. This limitation is not only of distance, but also of the nature of space and time. As the universe expanded after the Big Bang, the maximum distance we could observe grew. But due to this rate of expansion, regions of space are moving away from us faster than the speed of light. Therefore, there will always be parts of the universe that light cannot reach, a phenomenon known as the cosmological horizon. The observable universe itself is only a fraction of what it is. Beyond this horizon lies space filled with galaxies, stars, and other cosmic phenomena that we have never seen before. These regions are theoretically part of the universe, but are inaccessible due to the limitations imposed by cosmic expansion. Understanding the observable universe helps bridge the gap between what we know and what is beyond our current understanding. The limitations remind us that there is still much to explore, pushing the boundaries of space knowledge into regions our instruments may never reach. Our understanding of the observable universe has evolved dramatically over the centuries, reflecting advances in technology, mathematics, and scientific theory. In ancient times, people viewed the cosmos through a geocentric lens, believing that the Earth was the center of all celestial movements. Observations were limited to the eye, and the universe appeared to be a vast expanse of stars. But this perspective changed with the work of astronomers such as Nicholas Copernicus, who proposed the heliocentric model, placing the Sun at the center and ultimately broadening our view of our place in space. The invention of the telescope in the 17th century was a turning point in astronomical observation. Galileo Galilei's use of this new technology revealed craters on the moons orbiting Jupiter, and the phases of Venus, shattering the concept of a perfect and unchanging sky. As telescopes improved, so did our ability to detect distant galaxies, which led to Edwin Hubble's discovery of the expanding universe in the early 20th century. This discovery changed our understanding of space, giving us a deeper appreciation of its vastness and the relationships between celestial bodies. Technological advances in modern times have allowed us to look at the universe even better. Satellites, such as the Hubble Space Telescope, and missions such as the Cosmic Background Explorer, have provided information on the cosmic microwave background radiation, essential to understanding the early universe. Through these observations, scientists developed the Big Bang theory, shaping our view of cosmic evolution from the initially hot and dense state to the vast and cold universe we observe today. This growing understanding reflects not only the dynamic nature of scientific inquiry, but also the impact new discoveries have on our understanding of the universe. Each advance in our observational capabilities continues to challenge and refine existing theories, revealing that the observable universe is more complex than previously imagined and inspiring further exploration of space beyond our current limits. Current estimates place the size of the observable universe at about 93 billion light-years in diameter. This measurement covers the great distances between the Big Bang and the Big Bang 13.8 billion years ago. However, due to the expansion of the universe, the regions that emit the light that allows us to observe them are now much farther away than when the light first appeared. The observable universe is not a static boundary. As the universe expands, our ability to see further into space increases, even though it is limited by the speed of light. So what we can observe right now is only a fraction of the entire universe. As new astronomical instruments and technologies are developed, our understanding of distances in space improves, allowing astronomers to refine these estimates. Interestingly, the observable universe represents only a small part of the universe, which could be much larger or infinite. Some theories suggest that there may be other regions of space beyond what we see, from which light has yet to reach us, hinting at space filled with unknown territories. These estimates continue to evolve as we gain a deeper understanding of cosmic expansion and improve our observational techniques. Each insight adds a layer to our knowledge and sparks curiosity about what lies beyond the boundaries of our observable universe. Measuring distances in the observable universe is a complex endeavor that uses a variety of techniques and methods, each adapted to different scales of cosmic distances. For nearby objects, astronomers often use a method called parallax, which involves tracking the Earth's orbit around the Sun against the backdrop of distant stars. By measuring this shift, scientists can calculate the distance to the star using simple geometry. This method is most effective for stars within a few hundred light-years from Earth. As distances increase, astronomers turn to specific candles, which are objects with a certain brightness, such as supernovae or variable stars called Cepheid variables. Astronomers can determine how distant these objects are by comparing their observed brightness with their intrinsic brightness. Supernovae, in particular, serve as powerful tools because they can be observed at great distances, measuring billions of light-years. At even greater distances, scientists use the redshift of light, which is the phenomenon that light's wavelengths stretch as it moves away from us. The farther away an object is, the faster it appears to be moving away due to the expansion of the universe. By analyzing the amount of redshift, astronomers can estimate distances based on the relationship between redshift and distance, governed by Hubble's law. This method is essential for mapping the large-scale structure of the universe and understanding its expansion. Combining these techniques provides a comprehensive framework for space travel. With advances in technology and observational capabilities, our ability to accurately measure these dimensions continues to improve, helping to better understand our universe and our place in it. Each new discovery allows us to take a closer look at space, revealing its vastness. The most distant objects we see in the universe are galaxies and gamma-ray bursts, some of which formed when the universe was part of the modern era, about 400 million years after the Big Bang. One of the best-known galaxies is GNZ11, observed at magnitude 11.1, about 13.4 billion light-years from Earth. This galaxy provides important information about the conditions of the early universe, allowing astronomers to study how galaxies formed and evolved. Another remarkable category includes gamma-ray bursts, which are extremely energetic bursts that can outshine entire galaxies. The most distant gamma-ray burst is GRB 2012-120A, observed at a redshift of around 15.2. This explosion occurred when the universe was about 500 million years old, giving scientists a wonderful opportunity to study phenomena from the time when the first stars and galaxies formed. In addition, the Hubble Space Telescope and other observational instruments have detected ancient massive galaxy clusters such as MAX J1149 and 5+2 expanding our view of the past. These clusters not only help astronomers study the early universe, but also help us understand cosmic evolution and the distribution of dark matter. These observations demonstrate the amazing capabilities of modern telescopes and advances in technology. Each discovery of distant objects allows researchers to piece together a timeline of the universe, providing valuable information about its formation and the processes that shape the cosmos we observe today. Beyond the cosmic horizon of our observable universe remains a great mystery. This region consists of regions of space from which light has not been able to reach us since the beginning of the universe. Although this limits our ability to observe, many scientists speculate about what might happen in these unseen regions. Beyond our observable universe, there may be galaxies, stars, and space structures similar to what we see, but we have no direct evidence of their existence. Theoretical models show that the universe is expanding infinitely beyond what we can observe. In this case, regions of space can be filled with skyscapes that reflect structures within the observable universe. This means that countless galaxies, with billions of stars and potential planets in each galaxy, may exist without our knowledge. This concept raises the question of the fundamental nature of space and whether other life forms could exist in this potentially infinite space. Additionally, some theories consider the possibility of multimedia, where our universe is one of many independent entities. Each universe may have different physical laws, stability, and structure. This concept is still speculative and a topic of debate among physicists, and it raises interesting questions about the nature of reality and our existence within space. The regions beyond the space horizon remind us of the limits of our understanding and the uncertainties that lie at the forefront of space exploration. With every advancement in technology and methodology, the desire to explore and understand these uncharted territories in space grows, driving the search for knowledge about what lies beyond what we can see. Outside of our observable universe, the nature of space can be distinguished in many interesting and fascinating ways. One possibility is that there may be different galaxies and star systems in regions beyond our understanding, some of which exhibit completely different structures or compositions compared to what we observe. For example, these regions may contain galaxies that formed under unique conditions that we do not yet understand, leading to a diversity of cosmic landscapes that include unusual formations or skyscapes. Additionally, there may be different physical laws or stable regions, especially if theories like the multiverse have any credibility. In a multiverse scenario, different universes may exhibit completely different conditions, including variations in fundamental forces, the speed of light, or the behavior of gravity. This can not only change the types of stars and galaxies that form, but also affect the basic building blocks of matter, giving rise to exotic particles or forms of energy unmatched in our observable universe. In addition, the distribution and behavior of dark matter and dark energy, the dominant composition of the universe, may be different in these invisible regions. Although we understand very well the effects of dark matter on observable galaxies, its nature and behavior may reveal unexpected surprises. Different concentrations or properties of dark matter may lead to unusual celestial bodies, or ultimately change the dynamics of cosmic expansion in these regions. Understanding how these regions differ from our observable universe can shed light on questions about the origin, evolution, and ultimate fate of what we know. Every new discovery in the observable universe reminds us of the limitations of our knowledge, sparking curiosity about what might await beyond the limits of our understanding. The potential for different cosmic realities sparks the imagination and fuels the drive for further exploration and discovery. Cosmic inflation is a theory that proposes a rapid, exponential expansion of the universe within the first fractions of a second in the moments after the Big Bang. This theory was developed to solve several puzzling questions about the homogeneity and isotropy of the observable universe. According to the inflationary model, the universe expanded at an astonishing rate, stretching from subatomic scales to macroscopic distances, eliminating disorder in its fabric. This inflationary phase is thought to have produced the relatively uniform distribution of matter and radiation we observe today. The meaning of cosmic inflation is beyond our observable universe. One of the main implications of this theory is that regions beyond the cosmic horizon may have undergone the same inflationary process, leading to convergence on large scales. Because inflation is so fast, large regions of space are beyond our ability to observe or detect, leading to a scenario where significant parts of the universe are inaccessible to us. This means that even if there were any changes in density or structure in those regions, they would be beyond our reach due to the finite speed of light. In addition, inflation introduces the concept of a potentially infinite universe. If inflation is not localized to our visible universe, but instead affects a larger space, this suggests the possibility of an infinitely vast cosmic landscape beyond what we can see. Each region likely underwent its own inflation process, creating separate pocket universes, sometimes called bubbles, each with different physical characteristics. If this is true, it could mean that other parts of the universe may have different fundamental constants, or even different physical laws. The concept of cosmic inflation raises profound questions about the structure and nature of the universe in general. It prompts us to explore things beyond our observable horizons and invites speculation about the properties of the realms that remain hidden. This framework encompasses not only our own universe, but also the potential diversity of reality beyond our observational capabilities. The concept of multiple universes originates from theories related to cosmic inflation and the multiverse. According to these ideas, our universe may be just one of many, each with different physical properties and laws. During the inflationary phase after the Big Bang, some regions of space could have stopped inflation while others continued to expand, resulting in bridges of space-time representing separate universes. These multiple universes may show major differences. For example, some may have physical constants that differ from those in our universe, leading to variations in the types of matter or forces present. Such diversity could lead to completely different galaxies, stars, and even potential life forms. This concept expands our understanding of reality to include things beyond our observable boundaries. Although the existence of multiple universes is theoretically possible, it remains speculative due to the lack of direct observational evidence. Many scientists are working on ways to gather data that lends credence to various theories. For example, the cosmic microwave background radiation may contain evidence of the inflationary period and collisions between our bulk universe and others. Traces of such space events may be detected by current or future observational technologies. The idea of multiple universes tantalizes the imagination and invites us to explore the fundamental questions of existence. Although we cannot directly observe these spheres, studying the implications of their existence complicates our understanding of the cosmos and prompts further investigation into the fabric of reality. Every multiverse theory mentions the great uncertainties that persist in our quest to understand the universe and our place in it. In regions beyond the cosmic horizon, the laws of physics may defy our understanding of the universe as we know it. If we consider the possibility of multiverses or regions, each universe may operate under its own physical laws and stability, different from those of our observable universe. For example, fundamental forces such as gravity or electromagnetism may have different strengths, leading to completely different behavior of matter and energy. One interesting scenario is the cosmological constant, which is associated with dark energy and affects the expansion of the universe. In other regions, this constant can take different values, potentially leading to higher rates of cosmic expansion. Such differences can also affect the formation and stability of structures such as galaxies and stars, creating environments that differ dramatically from our familiar cosmic landscape. Additionally, the basic particles that make up matter can take different forms or combine in unique ways, resulting in alternative substances and energy. Some areas may have entirely new forces or interactions, but must be observed in our universe. This can lead to exotic physical phenomena or conditions that defy our scientific theories, pushing the boundaries of understanding of modern physics. Although these concepts remain speculative, exploring potential differences in physical laws beyond the cosmic horizon sparks an imaginative inquiry into the nature of reality. They raise important questions about the limits of human knowledge and the fundamental structure of the cosmos. As scientists continue to probe the interior of our universe, the possibility that other regions operate according to different rules points to the quest to unlock the mysteries of life. The many worlds interpretation of quantum mechanics is a theoretical framework that states that every quantum event causes the universe to spread into many parallel realities. This explanation was first proposed by physicist Hugh Everett III in the mid-20th century. In conventional quantum mechanics, particles exist in superposition states, where they can exist in multiple states at the same time before being observed. The act of measurement seems to bring this superposition to a single conclusion. However, the many worlds interpretation implies that all possible outcomes actually occur, albeit in separate, non-communicating sectors of the universe. According to this explanation, every decision or random event creates a split in the fabric of reality, leading to multiple parallel universes. For example, if you flip a coin, you may see one universe land heads and another land tails. Each of these outcomes exists in a unique universe, meaning that all possible outcomes of quantum measurements coexist and are equally real. One of the most interesting aspects of the many worlds explanation is how to avoid the notion of wave function decay, a controversial topic in quantum mechanics. By removing the need for abstraction, the theory solves several philosophical and conceptual problems related to observation and measurement. Instead, reality is seen as a vast, complex structure of diffusion paths where every decision and chance creates a new reality. The many worlds explanation remains one of several competing explanations for quantum behavior that has interesting implications for our understanding of reality and the nature of life. It challenges our preconceptions about determinism, free will, and the nature of time, and invites us to think deeply about the consequences of quantum events not only in our universe, but potentially in countless others. As scientists continue to explore the implications of quantum mechanics, the many worlds explanation is a bold and exciting possibility in theoretical physics. The concept of parallel universes is deeply connected to the multiverse theory, which holds that beyond our observable universe, there is a vast collection of universes, each with its own characteristics and laws. Although the term parallel universes often implies the existence of an alternate reality that is controlled by our own, the multiverse theory covers a wide range of possibilities, including different shapes and structures of the universe. In the context of multiverse theory, parallel universes can arise from multiple models. One popular approach is rooted in the many-world interpretation of quantum mechanics. Here, each quantum event leads to the creation of a new universe, showing all the possible consequences of that event. This means that for every decision made at the quantum level, a separate universe accounts for all potential paths, resulting in an interconnected web of parallel realities. Another aspect of the multiverse theory is related to cosmological models, especially cosmic inflation. In this scenario, our universe was one of many regions experiencing inflation. Each region can expand differently, leading to changes in fundamental physical laws, structures, or constants. These inflated regions can become their own separate universes within a larger multidimensional framework. In addition, some theories suggest categories such as line theory landscape, where a large array of vacuum states leads to many universes with different fundamental forces and particle types. Each universe can support a unique physical reality and allow for different configurations of time. Although each of these concepts represent different aspects of the multiverse theory, they all share the basic idea that our universe is not a single reality. Exploring parallel universes within a wide range of multimedia fuels the imaginative exploration of existence and enables a variety of experiences in different realms. It invites us to rethink the universe, reality, and even the nature of life within an infinitely complex cosmic realm. The theory of eternal inflation extends the traditional model of cosmic inflation, which describes the rapid expansion of the universe shortly after the Big Bang. Perpetual inflation assumes that the process of inflation does not end everywhere at the same time. Conversely, some regions of space may continue to inflate indefinitely, while others may stop inflation and become observable universes. Essentially, this ongoing inflation could create a scenario in which inflated regions continuously form, leading to a large and possibly infinite diversity. In this framework, the universe is viewed as a dynamic environment in which different regions can experience inflation at different rates. While parts of the universe cooled and settled, forming galaxies and stars, other regions remained in a constant state of inflation. Hence, new multiverses are constantly forming, each with different physical laws or constants. As a result, perpetual inflation supports the idea of multimedia filled with different realities that operate independently of each other. Eternal inflation further reinforces the multidimensional concept that our observable universe is just one tiny speck in the vast cosmic landscape. The implications of this theory suggest that environments in our universe may adopt completely different conditions, so that some may retain unique structures, fundamental forces, or even different dimensions of time and space. Additionally, the nature of eternal inflation suggests that this process is not a one-time event, but a dynamic system that continuously shapes the universe. This opens the door to the possibility of an ever-growing multiverse, where each bridge universe represents a snapshot of reality shaped by specific circumstances. Finally, the theory of eternal inflation combines the ideas of cosmic expansion and multidimensionality to provide a framework for understanding the vast complexity of the cosmos. It challenges our conventional view of the universe, invites us to consider the existence of unobserved realms that may operate according to completely different rules, thus enriching our understanding of reality. The landscape multiverse theory emerges from a theoretical framework that attempts to reconcile quantum mechanics and general relativity, suggesting that the fundamental particles of the universe are not point-like, but rather one-dimensional lines. Within line theory, the landscape concept represents a multitude of vacuum states, each corresponding to different configurations, physical constants, and forces. These vacuum states determine the properties of the resulting universe, leading to different realities. Compactness of additional dimensions plays an important role in line theory. Although our observable universe has 3 dimensions of space and 1 time, string theory suggests additional dimensions that are compact and unobservable. Landscape multimedia theory suggests that the configuration of these extra dimensions can produce an astronomical number of vacuum states. In fact, the estimates are based on 200 different probabilities in 10 different orders. Each of these configurations leads to stable physical laws and values that govern the behavior of matter and energy. As a result, landscape multimedia theory posits that our universe is one among a realm of potential universes, each of which emerges from different vacuum states within this landscape. Some universes may have conditions suitable for life, while others may lack the necessary structures or forces to support it. This means that the fundamental properties that we observe in our universe, such as gravity or the mass of particles, are not universal truths, but rather specific results as a result of the particular vacuum in which we are trapped. The implications of landscape diversity theory are profound, pushing the boundaries of our understanding of reality and living nature. This raises questions about the fine-tuning observed in our universe, since many physical properties seem to be precisely calibrated for the emergence of life. In this context, the multiverse provides a potential explanation. If there are many universes with different characteristics, then statistically, at least one universe like ours has the right conditions for life to flourish. Finally, multivariate landscape theory and string theory provide a rich and complex view of space. The universe we perceive is one of many unimaginable realities, each influenced by the basic structure and fundamental principle of the cosmos. Line theory. Finding evidence of other universes is a difficult challenge that sets the limits of our understanding of modern cosmology. One of the leading ideas comes from the theory of cosmic inflation, which suggests that our universe underwent an exponential expansion immediately after the Big Bang. This rapid expansion can lead to a multitude of spacetimes, each of which can form its own universe with different physical laws and constants. Although we cannot directly observe these other universes, we can look for clues in our own. One proposed method involves studying the cosmic microwave background radiation, the faint wake of the Big Bang. Scientists analyze this radiation for patterns that indicate anomalies or interactions with other universes. For example, if two universes collide, it can leave a unique signature in the cosmic microwave background that we can measure. Detecting such disorders requires highly sensitive instruments and accurate data interpretation, but advances in surveillance technology hold promise for the task. Another interesting avenue is the mathematical basis of string theory. This theory suggests that there are many dimensions beyond the four we experience. Some physicists suggest that these extra dimensions allow other universes to appear in our own. Experimental efforts, such as those carried out in particle accelerators, seek to reveal evidence of these extra dimensions, which, if discovered, could prove the existence of the multiverse.
The James Webb Telescope in 2023 has given space travelers an invaluable gift. The observatory's scientific program Cosmos Webb has created a unique brain image of 25,000 galaxies, the best guide to the galactic expanse of the universe. There are objects for every taste: beautiful spirals, bright lenses, jellyfish, and light bulbs. In this celestial guide, you can find any route for the most discerning travelers. But this is only 4% of the data that astronomers are going to get in the course of the entire project. They intend to map the earliest structures of the universe and conduct an in-depth study of 1 million galaxies. That sounds like an incredible number, but it would cover just 0.6 square degrees of sky, which is roughly equal to 3 full moons. However, scientists are constantly finding new galaxies, and each one is unique in its own way outside the cosmic web. There are beautiful flowers and colorful fireworks, scary zombies and cannibals, mysterious Yeti. That's where our space journey today is going to be. Oh, and at the same time, we'll see if the Milky Way really is a luminous spiral, as is commonly believed. Astronomers have some doubts about it. To find out, let's quickly continue on our way. In space, there are many structures that look like blurred clouds with stars inside. There are galaxies and nebulae that look almost identical from Earth. But we are interested in the first. And in order not to get lost, let's define the differences between galaxies and nebulae. Until the 20th century, astronomers didn't know there were galaxies other than the Milky Way. All the other bright spots in the sky were classified as nebulae, what any long-lived astronomical objects were called. According to this definition, many galaxy star clusters have fallen. For this reason, our neighbor, the Andromeda Galaxy, used to be considered a nebula. It was only in the 1920s that astronomer Edwin Hubble found out that Andromeda is actually a galaxy. The development of astronomy and the improvement of telescopes allowed to more accurately determine the difference between these objects of distant space. Now, galaxies are considered gravitationally bound systems of stars, star clusters, interstellar gas and dust, and planets. And nebulae are those parts of the interstellar medium that stand out against the sky. Galaxies, each containing an average of about 100 billion stars, vary greatly in size. There are dwarfs with less than 100 million luminaries and supergiants with 100 trillion luminaries. Take a look at the Alkean galaxy about 3 billion light-years from Earth. On the surface, it's just a bright spot in the sky with twinkling stars. But astronomers consider this object a true cosmic monster. Alkeans were discovered in 2022 in the constellation Rhys. The number of giant stars has not yet been accurately calculated, but it can be estimated based on the already known mass of the galaxy, 240 billion solar masses, so there could be billions of stars in the Alkean galaxy. In telescopes, it can be seen as a star orbiting a core with a supermassive black hole at its center. This hole ejects from the heart of the galaxy colossal jets of glowing gas and dust in the form of multicolored blades or petals. Such jets, when interacting with the intergalactic medium, accelerate electrons that produce radio emission. They turned the giant into a radio galaxy 16.3 million light-years across. How do stars manage to gather in such huge companies and stay together for billions of years? Scientists don't yet know all the nuances of galaxy formation, but it didn't really start with stars. About 300,000 years after the Big Bang, the universe, which then resembled a hot soup of elementary particles, charged electrons and protons began to combine with each other. They formed hydrogen and helium atoms. Almost all hydrogen was neutral, but ionized and easily absorbed light. Stars didn't exist at that time, so it's called the Dark Ages. Gases and dust gradually appeared. Among the gas and dust clouds of the early universe, some matter thickened and began to stick together. Their gravity was stronger than in other parts of the cloud and attracted new matter. This resulted in the precursors of galaxies, proto-galaxies. These formations were also heterogeneous in structure, forming clumps of matter in places. These formed protostars, which eventually started thermonuclear reactions within themselves, bursting into flames in the sky. Gravity formed the first galaxies when the universe was 400 million years old, or less than 3% of its current age. Their ancient origin was confirmed in 2023 by the James Webb Space Telescope. Astronomers used it to find the ultra-faint galaxy JD1. A faint object helped us observe the gravitational lensing effect. The Abell 2744 galaxy cluster acted as a lens. This object refracted the light of the more distant JD1, allowing it to display 13 times brighter than normal. It turned out to be a true celestial mammoth, as it emerged just 480 million years after the Big Bang. The age of the universe, then, was only about 4% of its current age. But were all galaxies formed at the dawn of the universe and since then live peacefully each in its own corner of the sky? Recently, scientists have found confirmation of the version that the formation of such objects continues, and now. At least astronomers have found HSC J 1631 plus 4426, which is only a few million years old. It is quite young by cosmic standards. The galaxy is located 430 million light-years away in the constellation Hercules, and differs from most others in the composition of its stars. Her star contains 62 times less oxygen than the Sun. This is the minimum value in the history of observations. Like other chemical elements heavier than helium, oxygen is synthesized in interstellar cores through thermonuclear reactions. This low O2 content suggests that most of the luminaries that make up HSC J 1631 4426 are very young. Another interesting feature of the galaxy is its extremely low mass, 100,000 times smaller than the Milky Way. It looks more like some globular star clusters than galaxies, even dwarf galaxies. The discovery confirms that new galaxies are still forming in our universe. At the same time, this process is gradually coming to an end. The expansion of the universe causes the density of matter to decrease. Because of its absence, there will be no new galaxies. One might even speculate that HSC J 1631 4426 is a member of the last galactic generation. But there was something about this theory of galaxy birth that literally shattered the whole picture. In the late 1970s, astronomer Vera Rubin studied how such objects rotate. It turns out that Andromeda behaves somewhat strangely when moving. Apparently, contrary to the laws of physics, the matter at the edges of the galaxy was moving as fast as in the center, and it shouldn't be. For convenience, insert a vinyl record into your turntable. You'll see that it spins faster in the center than it does around the edges. Nothing like this happened in the galaxy. This means that either Newton's and Einstein's physics doesn't work, or the edges of the galaxy are filled with some other invisible matter. It wasn't called dark matter because of its color. Rather, it was compared to a dark horse, since nothing was known about this hypothetical substance. Well, besides the fact that ghosts don't emit, reflect, absorb light or other types of electromagnetic radiation. X-rays, radio waves, and ultraviolet light pass through the dark matter and do not make contact with it. Astronomers now think that almost all galaxies not only contain dark matter inside them, but are surrounded by its huge invisible halos. It is believed that in the early universe, giant dark curls served as a gravitational framework of ordinary matter to build the first galaxies. One of the best evidence for the existence of dark matter astronomers consider the galaxy Cluster 1 I065756, or BALL. It was formed after the collision of two large clusters of galaxies. Scientists believe this is one of the largest events in the universe since the Big Bang. The scale of the catastrophe has given science the opportunity to learn a lot about galaxies. The main components of the cluster are stars. Gas and invisible dark matter behave differently during a grand collision. Because of this, scientists were able to study each cosmic object of Cooley separately. They discovered that there was a lot of dark matter in the galaxy. To catch the invisible was very difficult, and here again helped the method of gravitational lensing, that is, illumination at the expense of background objects outside the galaxy. But the orb is just a kingdom of light compared to a very dim dragonfly. Astronomers believe that dark matter makes up 99.9% of its mass. The amazing celestial dragonfly resembles a dwarf galaxy in terms of the number of stars. The size of the Milky Way is enormous. The bright, hot gas from which stars are born seems to be virtually absent in Straka's 44. And only the skeletons of old stars fill the galaxy with a faint glow. The opposite of this dim galaxy is NGC 1052 DF2 and the constellation Keith, located 62 million light-years from Earth. Take a look at this picture of the Milky Way. You are unlikely to notice anything special about it. Well, except for the photo glittering with lots of stars. Indeed, NGC 1052 DF2 has hundreds or even thousands of times fewer stars than a similarly sized Milky Way. The trick of the strange galaxy isn't even that, though. There's no dark matter in it at all, just like its neighbor NGC 1052 DF4. In this regard, scientists are still only making assumptions. For example, nearby larger galaxies have been pumping gas out of DF2 and DF4. They've now been detected in parts of their smaller neighbors, and in the latest study, cosmologists have suggested that the two dwarf galaxies collided with each other about 8 billion years ago. This event caused their gas to split up and form many new, even smaller dwarfs. At the same time, DF2 and DF4 had no dark matter. Now it's up to them to somehow survive like this without a skeleton, and even maintain their shape. So NGC 1277 looks like a cosmic lens. We'll talk more about what these are. In the meantime, let's note that there are galaxies of many different configurations. Each one of them has its own unique properties. Let's go to the most interesting galaxies of different shapes to uncover their marvelous secrets. Let's start with spiral galaxies. If only because in this case you do not need to fly anywhere. Our Milky Way is a classic spiral galaxy with a junction. We can't look at it directly from the outside, but scientists have figured out what our world looks like based on models and calculations. Like other celestial spirals, they are a strange, flat, blue-white disk of stars, gas, and dust with a yellowish bulge in the center. They're crossed by a bridge, a band of the brightest stars. The arms of the galaxy, like other similar objects, start from the end of the nucleus, not the bulge. The Milky Way is actively igniting stars. The gas may have entered the core through these casings. It contains about 200 billion luminosities and has a total mass of about 600 billion solar masses. But we won't stay on the Milky Way for long, because we know it well enough. Although, recently Polish scientists voiced an incredible theory. The Milky Way doesn't look the way it's commonly thought. Astronomers have analyzed the galaxy's brightest stars. Research has shown that it is not flat, as previously thought, but twisted and curved. Researchers believe that the Milky Way could have changed shape due to past interactions with nearby satellite galaxies, intergalactic gas, or dark matter. However, this theory has not yet been tested, and the Milky Way remains to us still the same marvelous spiral shining in the sky. Many other galaxies of this type look like it, but not all of it is. To see for yourself, let's head to the constellation of the Dragon, where a veritable tadpole floats across the sky 300 million light-years from Earth. At least one of the spiral galaxies in this constellation is very similar in shape. At one end of the galaxy, many stars cluster together to form a head, and the rest stretched out a long tail at a distance of 500,000 light-years, which is 10 times the diameter of the Milky Way. The celestial tadpole contains a huge amount of gas mixed with several clusters of bright blue lights, so it stands out well in the sky. Perhaps two disk galaxies dragged a smaller dwarf galaxy behind them and formed a space object of such a strange shape. Scientists are still not fully convinced of this version and are looking for other reasons for the birth of a strange tadpole in the sky. Recently, the Hubble telescope was able to spot clumps in its tail. These are supermassive clusters 4 to 5 million years old that will eventually become dwarf satellites of the main galaxy. But it seems it's not just astronomers who study space. If we fly in the constellation of the Big Dog at a distance of 114 million light-years, we will see a huge eye in the sky, similar to the Eye of Sauron from The Lord of the Rings. And next to it is another smaller eye. It is observed in the sky an unusual pair of spiral galaxies, IC 2163 and NGC 2207. They look like eyes with very bright pupil cores. Their two very elongated arms surround the pupils like eyelids. In the past, scientists say, the galaxies were common neighbors. However, relatively recently, they maximally approached and began to literally scratch each other. This event caused gravitational tsunamis that rush from the edges of the galaxies to their centers at a speed of 100 kilometers per second. The motion of these waves agitates the interstellar gas and causes thousands of new stars to form in it. The waves themselves lose energy over time, colliding with denser clumps of gas and compacting them further. They spiraled, moving around the center of the galaxy and forming stellar eyelids. The eye galaxy, of course, doesn't actually see anything. Otherwise, it would surely envy the beauty of Messier 63 in the constellation Hound Dog. This spiral object is 57 million light-years away from our planet and looks like a sunflower from a Van Gogh painting. It consists of a central disk surrounded by short spiral arms, petals of blue and white stars. The cosmic sunflower has the unique ability to constantly change color. Astronomers always see its center bright yellow and its petals sometimes milky white, sometimes purple, blue, or brown. But the coolest, perhaps, is the galactic connection of the two hearts. We'll see it in the constellation Pegasus, 400 million light-years from Earth. There, at the center of the galaxy, NGC 7674, are two supermassive black holes very close to each other. Their total mass reaches an incredible 35 million solar masses. Perhaps the galaxy acquired a spare heart by attracting to its center the black hole of a neighboring black hole with which it merged in the distant past. Now its hearts are burning in huge jets. These jets of red-hot plasma fly out of both black monsters. Then they merge into a single giant stream, as if symbolizing the union of both galactic hearts. Elliptical galaxies are no less strange and diverse, accounting for about a third of all known galaxies. Their shape is mostly true to their name, but often varies from nearly round to elongated cigar-like shapes. Regardless of configuration, elliptical galaxies are older. They contain relatively little gas and dust, so they rarely ignite stars. There are hardly any young, hot, and bright lights in them. They are mostly filled with old and relatively cool stars like red giants. The color of such galaxies is correspondingly most often reddish. Stars orbit around the centers of elliptical galaxies just as they do in spiral disks, but they do so in more random directions. The masses of such objects range from hundreds of billions to a few million solar masses. This is a wider mass range than other types of galaxies. Speaking of dwarfs, some of them are part of the local group of galaxies, including Andromeda's companions NGC 205 and M32. The largest and rarest are about 300,000 light-years in diameter. Astronomers believe they formed from the merger of smaller galaxies. Their dark halo crowns are so large that they reach their neighbors. These giants often contain globular clusters of hundreds of thousands of stars. On average, the higher the mass of an object, the more globular clusters it has. Isolated elliptical galaxies are very rare. The masses of black holes in the most massive galaxies reach values of several billion solar masses. Galactic gas enters the neighborhood of black holes, stimulating the activity of the nuclei, and they turn into powerful sources of energy. Sometimes these processes are accompanied by the ejection of streams of charged particles from the center, making them powerful sources of radio emission. The nearest elliptical galaxy of this type, NGC 4696 from the constellation Centauri, strikes astronomers primarily by its shape. It is neither a sphere nor an ellipse, lacking the characteristic arms and colors of spiral galaxies. The galaxy is a huge band of dust with a diameter of about 30,000 light-years. Within it, strange thin filaments of ionized hydrogen can be seen. The matter in the fibers is 10 times denser than the surrounding gas. These strange structures create a slightly noticeable marbling effect in the galaxy's bright center. It's hard to imagine the violent events taking place among these layers of dust. It is believed that at the center of NGC 4696 is a supermassive black hole, ejecting jets of matter at near-light speeds. X-ray images show huge voids inside the galaxy. Astronomers see them as clear signs that superjets are ejecting a central black hole into space. A more active object is 12 billion light-years away from Earth in the constellation Sextantus. This is the brightly colored Baby Boom galaxy, a veritable stellar nursery. Ellipses are thought to burn slowly into stars because of the small amount of gas and dust they contain. But it's full of content because it's similar to its lazy counterparts. The insanely prolific galaxy manages to give birth to a star every 2 hours, while the Milky Way, for example, takes 36 days to do so. In other words, the Baby Boom gives birth to 4,000 stars a year. Our galaxy is only 10 years old. It would only take 50 million years for this glowing factory to become the most massive ever observed. According to astrophysicist Peter Kapak of NASA's Science Center, if humans procreated so intensely, everyone alive today would be the same age. There are hybrids in the sky that look like elliptical and spiral galaxies. They're called binaries because they actually resemble lenses. Like spiral galaxies, the objects have a thin rotating stellar disk and a central bulge, although they do not have arms. Lenticular galaxies are also spiral galaxies. However, their core compared to the disk is much larger than that of spirals, accounting for 50% of the total size. 2/3 of lenticular galaxies, like leptic galaxies, contain little dust and interstellar matter. Their population consists mostly of ancient red giants. The remaining third contains a lot of gas, like spiral galaxies, and likely contains young stars. A new Hubble Space Telescope image shows what a typical lenticular galaxy NGC 6684 in the constellation Centauri looks like. This faint object resembles a real cosmic ghost. And that's because NGC 6684, due to the loss of much of its gas, is virtually no longer forming stars. The pale galaxy was first discovered by astronomer John Herschel in 1836, but Hubble was able to get a great look at all of its details. It turns out that NGC 6684 resembles a ghost due to the lack of dark dust lanes typical of other galaxies. The lenticular ESO 381, 12 in the constellation Centauri, 270 million light-years away from Earth, is also faint, but not like a ghost. It looks more like a delicate flower blossoming against the cosmic void. Its graceful petals form even within the galaxy and extend beyond it. It's quite possible that the bloom was caused by a shock wave from a relatively recent galactic collision. And the lenticular galaxy in one of the latest images from the James Webb Space Telescope is not as marvelous as a flower, but it is more unusual. It resembles a fishing hook. The strange shape of the galaxy probably resulted from the gravity of the El Gordo cluster, which distorted the direction of light. In addition, the fishhook is distinguished by its original red-orange color. This is due to a combination of dust reddening within the galaxy itself and cosmic redshift due to its extremely large distance. Researchers determined that it took 106 billion years for the light from the fishhook to reach Earth. Astronomers also determined the diameter of the galaxy, 26,000 light-years, which is almost 4 times smaller than the Milky Way. And the birth of stars at its center is already in decline. But what if we see something strange during the flights? Not a spiral, not a lens, not an ellipse. Just some cloud with stars inside. Astronomers say that such galaxies are not a unique phenomenon. In percentage terms, they make up a quarter of all known species and are very diverse. Some have very faint hints of structure, most often spiral. Others have no shape at all. These chaotic objects are usually devoid of a pronounced core, spiral branches. Astronomers have singled them out as a special group and called them irregular. We don't have to travel very far to meet them either. Irregular galaxies include the large and small Magellanic Clouds surrounding the Milky Way. They appear deformed and devoid of a distinct shape. Mainly, their appearance is distorted by the gravitational influence of large nearby galaxies. Although the large and small Magellanic Clouds are more of an exception, most of the irregular galaxies observed by astronomers are on the outskirts of space. In the early universe, before other species appeared, there were many of these formless objects. They later formed as spirals or ellipses, and then some were deformed by gravitational forces. But in any case, they are lively regions of space. Most irregular galaxies are full of gas and dust, making them excellent breeding grounds for the formation of new stars. One of them is NGC 1569, a dwarf irregular galaxy in the constellation Giraffe. This dim, somewhat blurry object is not popular with astrophotographers, but is of great value to science. It is located 7.8 million light-years away, and by some calculations 11 million light-years from us. Scientists say that for the study, the galaxy is relatively close and very suitable for studying the history of star formation. The Hubble Space Telescope has already managed to break NGC 1569 into individual stars and learned a lot about each one. But the galaxy NGC 1156 is bright and original. It shines in the sky with a whole bouquet of red colors. They are formed by many bright young stars that have become something of an island and light up the cosmos. The galaxy's core, on the other hand, is made up of older luminaries. Interestingly, NGC 1156 is an isolated galaxy. It has no close neighbors whose gravity could affect its shape or trigger a burst of star formation. But the top of the irregular galaxies is shown in the famous image of the early universe obtained by the James Webb Space Telescope. The image covered a patch of sky about the size of a grain of sand that a person on Earth holds at arm's length. But the image shows thousands of galaxies as they were at the dawn of the universe. It is the oldest to have come into the Internet's lens due to its irregularly shaped gravitational lens. It is believed to be 135,000,000,000 years old. That is, we see the eye of Z13 as it was just 300 million years after the Big Bang. Astronomers have just begun to study this galactic relic, and one of the fashion brands has already managed to promote it. The unique image, dubbed the ultra-deep Webb field, was printed on fabric and created into a marvelous galaxy dress. The price of the product also turned out to be simply exorbitant. That's almost $80,000. In addition, there are many galaxies that don't fall into these categories. Most often, as astronomers say, such objects are in a transitional stage of their development. It used to be spirals, ovals, lenses, or just spots in the sky. And then, as a result of various internal or external processes, they acquired a completely strange appearance or unusual properties. A new image from the Dark Energy Camera project shows one such galaxy. It's about twice the size of the Milky Way, and it looks like an onion of paradise with 20 layers. This is NGC 3923, the constellation Hydra, located at a distance of 90 million light-years from Earth. Astronomers call such objects shell galaxies. They look like elliptical simulators but have significant differences. The stars in the heavenly onions are not evenly distributed, but are organized structures of separate layers. NGC 3923 is believed to have gotten its strange shape after merging with another galaxy. When the two objects began to merge, the gravitational field of the larger one slowly pulled the stars away from the disk of the smaller one. The stars of the latter gradually mixed with the outer halo of the more massive galaxy, forming concentric bands or shells. A simple analogy: add a drop of food coloring to the bowl of dough you are slowly kneading. The blob will stretch out in a spiral, which would remain visible for a long time before completely dissolving into the dough. Similarly, the stars were distributed between the layers of the halo. There's another theory. The unusual shape of the galaxy could be the result of a massive white dwarf exploding inside it. And if we see something like a jellyfish in space, it means that we have also found the attraction we need. Astronomers classify such objects as a separate group, and there are over 400 of them. The strange shape of the jellyfish is probably due to the fact that they travel at unimaginable speeds in galactic clusters. When they collide with intergalactic gas, some of their matter is ejected into space. This matter forms a kind of tentacle, speakers tens of thousands of light-years beyond the galactic disk. It's in them that star formation is active, so the tentacles are usually very bright. And, as it turns out, jellyfish aren't just amazing for their shape, they have a completely unexpected property. Like couriers that bring us pizza, galaxies deliver gas from intergalactic clouds to black holes. An international group of astronomers noted the unusual activity of the centers of such objects. Among the 7 celestial jellyfish observed by astronomers, 6 have active galactic nuclei. It's much more than expected. Perhaps ESO 137, 001 from the Southern Triangle constellation, which astronomers are now studying, has a similar property. In appearance, it is a real bluish jellyfish with blue tentacles the color of its stars. It moves in a cluster of galaxies, ABL 3627, with a strong gravitational pull filled with glowing plasma.
Do you want to go on a celestial poltergeist or an expedition to the axis of evil? Like something loud and deadly, but it's unlikely that any of our space travelers will turn back in fear. We are willing to overcome any difficulties to learn more about the universe. In fact, Poltergeist is the name of planet PSRB 1257, 12C, 2,300 light-years from the Sun in the constellation Virgo. He has only the conditions of hell. A poltergeist is showering deadly ions from a nearby star, a pulsar. But there are no otherworldly powers, and the axis of evil is the direction in which galaxies and large space objects are aligned. If such a structure were confirmed to exist, it would disrupt the standard model of cosmology. This shows that space has no definite direction. However, there is no danger to space travelers. Instead, we suggest going to the edge of the universe, a world full of truly unexplored and insane mysteries. It will be a real space odyssey. Along the way, we encounter a deadly labyrinth from which we cannot escape, admire a beautiful butterfly, and cross the territory of strange cosmic threads that cause storms. But what awaits us in the finale? Are we going to run into some obscure wall? Will we face an evil force that destroys everything around us? Or will we see other amazing worlds? Anything is possible outside the universe. But before we set out, let us know how the edge of the world has been searched at different times. The starlit sky has fascinated people since ancient times. Our distant ancestors were eager to know what its shining fabric was made of, what form it took, and where it ended up. Answers were sought in relation to the earthly and familiar. The firm was often imagined as a carpet, decorated with stones or even a beautiful flower. The Egyptians, for example, believed that it was a lotus. Its essence is the center of the world where the gods live, and the world in the leaves is where people live. Hindu texts describe space as an egg, Dravetic, like an island floating in the endless void. Over time, more was learned about space, and perceptions changed. In 1610, Galileo Galilei pointed his first telescope at the sky. A famous astronomer discovered a cluster of countless stars. It is hidden in a band of light called the Milky Way. Then the outer space for humans increased infinitely. A century and a half later, in 1784 to 1785, William Herschel first attempted to determine the size and shape of our galaxy. The scientist concluded that the path of the Milky Way resembles a flat disk, but did not greatly estimate its diameter. Another century and a half later, when astronomers built powerful enough telescopes, the frontiers of space were pushed back for us. In 1924 to 1925, Edwin Hubble proved that the universe is not limited to our galaxy. The Milky Way turns out to be just one of many concentrations of stars, dust, and debris. Then came a new generation of advanced telescopes. Astronomers have seen with their help that the visible universe extends to incredible distances. There are about 2 trillion galaxies. Scientists have determined the age of the universe, otherwise known as the cosmic light horizon, or megalax. That's about 13.8 billion years. This is when light particles, photons, reach the Earth. According to American astrophysicist John Mutter, it is impossible to keep up with the age of the universe. When we look into deep space, we look back and see the distant regions of the universe, what they were a long time ago. Why can't we look back? The universe, according to the accepted theory, came into existence as a result of the Big Bang. The material exploded in diversity with unimaginable force and has been expanding ever since. During the very hot period before the galaxy formed, it was filled with hot, glowing gas and was therefore opaque. During the first million years after the Big Bang, as space expanded, the gas cooled to 10,000 degrees Celsius and glowed. This glow was originally ultraviolet, but as the universe expanded, it shifted to longer wavelengths. So today we observe it in microwave and infrared radiation coming from the edge of the metagalaxy. You can think of the source of the microwave background as a distant spherical wall. It limits the visible universe. We can't look at this wall yet. However, astronomers study the farthest reaches of the universe. They have shown us what awaits us on the way to the outer reaches of the visible universe. Of course, the positions of the celestial bodies observed by astronomers today have changed. The universe is expanding faster than the speed of light, and it is impossible to outrun it. Even the superfast stars of the future won't be able to. When flying through space, these things don't stop moving either. We do not know them. But let's imagine they found a way to travel fast through space. Well, for example, with a ready-to-go container that compresses space or compresses the structure of molecules. We can even determine our route in advance using a special map by Johns Hopkins University astronomers in the United States. This guide shows the positions of 200,000 galaxies stretching from our Milky Way to the farthest reaches of space. The data comes from observations from the Apache Point Telescope in New Mexico. Observatories have been probing various parts of space since 2000, allowing scientists to create the most complete maps of the observable universe. A map of U.S. scientists is a credential that looks like a slice of pizza. It provides the most accurate visualization of galaxies from the Milky Way to the edge of space. If the pointer to our coordinates were placed on the map, it would be placed at the sharp end of the 10-degree circle. It is part of the Great Circle around our galaxy, which in turn is a piece of the unimaginably large universe. According to scientists, from the beginning, the MUG was 13.7 billion light-years. Starting at its lower edge, the blue shows spiral galaxies 2 billion light-years away. The yellow dots are elliptical galaxies that are much brighter. The large red portion of the map also marks elliptical galaxies, but 4 to 8 billion light-years from Earth. Blue indicates quasars. Then comes a billion light-years of total darkness, a line that shows the edge of the visible universe at the end. This relic is a field of light, the light left over from the Big Bang solar system. We set out with the map. At the edge of the solar system lies the precious cloud. There have been no direct observations of this structure, but circumstantial evidence proves its existence. The charge cloud is thought to consist of two distinct regions, a spherical outer region and a disc-shaped inner region. They consist mostly of water, ammonia, and methane ice rocks. Astronomers believe that these objects formed in the early stages of the development of the planetary system near the Sun. Later, the giant planets hurled them into space with the force of gravity. We also have to maneuver among the trillions of long-period comets that are filled with precious clouds. After leaving it, we reach the boundary of the interstellar medium, where the heliosphere is located. This unique shell of the solar system, filled with plasma from the solar wind, orbits the star faster than the speed of sound. It is about 17.5 billion kilometers from the Sun. That is, twice as far as Pluto. So far, only the Voyager 1 and Voyager 2 probes have reached it. Retracing their tracks, our expedition may encounter strange and still unexplained phenomena. Scientists from Princeton University in the United States have discovered amazing structures and powerful waves in the space between the solar system and interstellar space. Data from the IBEX satellite show that a storm can rage over an area of about 1.5 billion kilometers. We will reach the edge of the solar system and see our world from the outside. What will it look like? To this day, astronomers believe that the solar system is like a long-tailed comet flying through space. The heliosphere is the large plume that stretches behind the star system as it orbits the galactic center. But recent models have suggested that the solar system may resemble a crescent-shaped bridge on the outskirts of the solar system. After the storms in the heliosphere, the calm interstellar space of the Milky Way awaits us. Or is it turbulent there, too? The further away from the galactic center, the more densely populated region of new luminaries, dwarfs, stars, and planets there will be. But they are also found on the edge of the Straw Road. The most unlikely star in the outer regions of the galaxy is WB 89-789. It was recently discovered by Japanese and Taiwanese astronomers. This newborn luminary is 62,000 light-years from the center of the Milky Way. Our Sun, by comparison, is twice as close to the galactic center. After the investigation, the protostars surprised the scientists. Observations made by the ALMA telescope in Chile show that the young luminaries are surrounded by an unprecedented variety of molecules. They contain carbon, oxygen, nitrogen, sulfur, and silicon. They also include complex organic compounds with up to 9 atoms: methanol, ethanol, methylformate, and others. They serve as raw materials for the larger molecules necessary for the formation of life. Who knows what fantastical creatures we might encounter in the WB 89-789 system? But what lies at the far end of the galaxy? Scientists say it is far from a desert region. Outside the galactic disk, the Gaia Space Observatory says, there are many large unseen structures. They look like some sort of large spinneret fibers. The authors of the study believe that they are remnants of the outer arms of the Milky Way. At various times, they were destroyed by galactic satellites, and now they themselves are destroying the environment. But fuzzy filaments may be far from the edge of the Milky Way, and not the most dangerous place on its periphery. A new study of 200 variable stars has revealed the outer limits of our galaxy. According to theoretical calculations, its edge was several tens of thousands of light-years from the center. So we're almost on a collision course with neighboring Andromeda. There is almost no space between galaxies. In this region, we can expect dangerous areas of turbulence, such as red-hot plasma, or something more unexpected. Once out of such a turbulent zone, it doesn't matter which way we fly. The standard model of cosmology holds that space has no definite direction. This is not a small area, but a huge area, hundreds of billions of kilometers in size. If you could see such a large piece of sky from Earth, say, from the planet Proxima in the constellation Alpha Centauri, the picture would not change appreciably. So we can go either way, from galaxy to galaxy, past universes, planets, stars, interstellar and intergalactic space, dark, empty, and cold. We may encounter some hellish places along the way. It is better to avoid them in order to avoid getting burned. These are primarily black holes, which are often referred to as real space monsters. They attract with their own gravity and can absorb any matter that comes their way. Fortunately, large objects are surrounded by bright accretion disks of red-hot plasma. Most recently, the supermassive black hole at the center of our Milky Way, the star A, is Sagittarius. Isn't it easy to find such a bright sign created by nature in space? And, of course, stay away. A bit tricky. This is essentially the space between the galactic filaments where the galaxies themselves do not exist. The largest of these are called superwoods. But what kind of danger could the voids of heaven pose? Let's take the large supervoid of Eridanus. This cosmic anomaly is incredibly distant, 60 billion light-years from Earth, in the constellation Eridanus. The supervoid is a fantastic size, 1.8 billion light-years across, almost to the edge of the visible universe. Compared to that, the Milky Way seems like a tiny invisible dot on the map. Its size is estimated to be only 100,000 light-years. So, supervoids could contain 18,000 galaxies like ours. A supervacuum is characterized by an unusually low microwave background. It is also very cold, a lower temperature than relic radiation. For this reason, astronomers have called the void a relic cold spot. Scientists believe that it formed at the end of the Big Bang, when the hot universe began to cool dramatically. This process can be compared to the appearance of air bubbles in ice. Generally, there is nothing in the supermassive universe that is believed to be filled with dark energy. This does not contradict the standard model of cosmology. If our first starship fell into the Eridanus supervoid, it would be the ultimate death trap. Relic cold is known as the darkest place in the universe. There are no stars or galaxies. Not one of its rays illuminates its infinite depths. Nothing can be seen, heard, or felt in such a place. Even with the coolest GPS, we won't be able to find our way out of infinite nothingness. We won't be going to amazing places like the supernovas, but we'll certainly be flying closer to the dome, whose brilliant glow, despite the great distances, astronomers observe Earth from. The most impressive is considered to be the Butterfly Nebula, or NGC 6302, in the constellation Scorpius. It is 2,500 to 3,800 light-years from Earth. Nebula's butterfly appearance is given by the dying stars at its core, which have spewed huge plumes of gas into space as they agonized. This gas, heated up to 20,000 degrees, passes through space at a speed of 100,000 kilometers per hour. But symbolizing the beauty of the universe is the architecture in the Eagle Nebula known as the Pillars of Creation. The fantastic pillars of the sky seem to be the creation of higher forces. In fact, they are filled with the same clouds of gas and dust that nature weaves with special skill. Their strange silhouettes are illuminated by intense ultraviolet light from the young, massive stars that cluster around them. Meanwhile, the cocoons inside the columns form new stars. But the real secret of the universe is revealed to us by the bright light of the Belle Nebula, which seems to be placed in the galaxy cluster C10024. 17. The nebula is thought to have formed during the collision of two giant titans, galactic masses. In a catastrophe, such giant clusters cannot be held together by the weight of their stars. They are probably held together by dark matter that forms a ring. Dark matter in general, composed of elementary particles, is still unknown to science. But distant galaxies in the C-100,024+17 cluster illuminated the cloud with their radiation. This celestial jewel is beyond the visible universe. You would have to travel 5 billion light-years to see it. Arundel, or the morning star, is even farther from Earth. He was indeed born at the dawn of the universe. The light that astronomers detected was emitted by a star 900 million years after the Big Bang. It is twice as hot as the Sun and 1,000,000 times brighter. Arundel has a mass of 50 to 100 times that of the Sun, and its surface temperature is estimated to be at least 20,000 Kelvin. The James Webb Space Telescope recently captured the most detailed image of Arundel yet. Above it, the star shines blue-white. It will be an unforgettable sight. But no one is going to see it for real. Even if by some miracle we were to drive Arundel while watching the video, we couldn't find anything in her place. The star died a long time ago. Such hot and bright stars usually don't last very long. They quickly burn up their hydrogen reserves, becoming supergiants and then supernovae. With the morning star, this may have been long ago, and its light, like an immortal avatar, still travels through space. We will go to another object in the outer universe, which will live for a very long time. This quasar J0313-1806 was discovered by astronomers at the University of Arizona in the United States. This was when the universe existed 670 million years ago. As we approach this space region, we will be amazed by the numerous celestial fireworks. First, the quasar itself is incredibly bright. It contains a supermassive black hole with 1.6 billion solar masses that emits giant streams of plasma, jets, and fuel. For astrophysicists, J0313-1806 is a rare find. Only two very distant quasars are known today. With their help, scientists want to test the theory of the formation of supermassive black holes in the early universe, as well as estimate their growth rates. In addition, J0313-1806 is the center of a galaxy that is shining stars with unprecedented activity. The birth rate of light is 200 solar masses per year. If you compare this to the rate of star formation in the Milky Way, in our galaxy it is equal to 3 solar masses per year. However, this is not a record in space. Galaxy Mamba 9 contains a large amount of dust and gas that prints out the stars one by one, like on a printer. The total mass of light produced in 1 year is more than 1,000 times the mass of the Sun. Mamba 9 was recently considered the most distant of the galaxies. According to research, it was formed 970 million years after the Big Bang. The distance from Mamba 9 to our solar system is 13 billion light-years. But now, this multi-star kindergarten has lost its record-breaking title. The I-galaxy Z13, discovered by astronomers with the James Webb Telescope, is 13.5 billion light-years from Earth. It was formed over 300 million years after the Big Bang. It's actually a space dinosaur, with a mass roughly equivalent to 1 billion solar masses. It is about 1,600 light-years across. True, from the outside, the galaxy does not look like a terrible lizard. When James Webb interpreted the telescope image from visible infrared light, the eye of Z13 looked like a stunning red flower with a white center. But is there anything else? It could happen. It would be a shiny wall. But you should not be upset, because the wall will not be able to block the way of our expedition. If you look closely, each bright spot in this amazing structure is a different galaxy. There are over 100,000 of them in this region. Scientists have calculated that the object has a quadrillion, that is 15 zero stars like our Sun. The Magadient structure is called the South Pole Wall and is 500 million light-years from Earth. The wall is astonishing in its size, even on a cosmic scale. It spans 1.4 billion light-years in space. For comparison, the size of the Milky Way is about 100,000 light-years. By measuring the redshift of the galaxies, scientists were able to detect the Great Wall. We know that everything in the universe is in motion. As they do so, their light waves are stretched, changing the light. By evaluating this shift in light, it is possible to understand what an object is and how it moves through space. Thus, scientists have found other similar objects. Compared to one of these, the South Pole Wall will seem like a short fence. The Great Wall of Hercules, the Northern Corona, a large flat structure of galaxies stretching 10 billion light-years into space. It makes up 10% of the entire observable universe and probably stretches to the end. So we've reached the edge of the metagalaxy for astronomical observations. We already know that it is 13.8 billion light-years. Here's how long it takes photons from the universe to reach Earth. But in the meantime, the universe continues to expand, and the object carrying the photons' information is being pushed into the distance by the expansion of space. The universe is thought to be 92 to 94 billion light-years in diameter from Earth to the cosmic light horizon for all time since its birth. This will be the edge of our universe. It can really be compared to a wall. There is darkness behind it because the relic radiation does not travel there. Does this mean that there is nothing in the observable universe? Could there be large galaxies, stars, and planets out there that are invisible to us? Or is there something more exotic, even terrifying? And is our expedition in danger of disappearing into the abyss of darkness? What are you thinking about? A. Is there any possibility of becoming nothing in the full sense of the word outside the universe? It's not a very pleasant prospect, but scientists allow this possibility. Based on this observation, galaxies are dying en masse in space. The Department of Astrophysicists of the International Center for Radio Astronomy Research said this after studying more than 11,000 objects. Researchers have come up with interesting theories to explain such a large-scale disease. One of them links the extinction of galaxies to vacuum decay. We now live in a world with stable energy levels. Scientists called this state a false vacuum and compared it to equilibrium. They suggest that one day, due to some shock or other event, such an equilibrium will appear as an energy depression. As a result, the energy level in the universe will drop to a minimum. Then the false vacuum begins to dissipate, giving way to the true vacuum. Perhaps this process is set in motion, and the vacuum eats galaxies at the edge of the universe. It is true that galaxies decay slowly, and vacuum decay should, according to physical laws, occur at the speed of light. It would destroy the Earth in seconds. Thus, our expedition is not threatened by a complete vacuum. By the way, you don't have to worry about the Earth anyway. Even if vacuum decay has begun at the edge of the universe, it will not reach us for billions of years. But suddenly, instead, we were caught in a vortex of crazy energy. According to one of the hypotheses, the galaxies can spread the most mysterious forces of the universe, the dark stream, the coordinated movement of galaxy clusters into an unknown mass in the invisible region of the universe. Scientists at the Goddard Space Flight Center, NASA, discovered these signs of the phenomenon. The theory was proposed based on the analysis of data from the WMAP survey in more than 1,000 clusters. This is a very large-scale study that covers a significant portion of the observable universe. The authors of the paper said that the dark stream stretches for 2.5 billion light-years. It rushes towards the supercluster of large galaxies, then towards the stars Centauri and Hydra. Scientists believe that this insane amount of snow could pull the entire universe into a black hole of unimaginable size. When the monster density reaches a critical point, a big bang will occur, and a new universe will be born. According to another, more exotic version, the black stream was formed as a result of the gravitational pull of some mass from a parallel universe. However, so far, these dire hypotheses have been largely unsupported. However, there are anomalies beyond the visible universe that alarm astrophysicists. Recent observations have shown that some astronomical objects do not move as they should. Hence, there may be unknown massive structures outside the metagalaxy. Their attraction affects the objects around them. Scientists call such hypothetical structures extra-metagalactic. Unfortunately, scientific methods to accurately determine their nature are still not available. The existence of such objects suggests that the universe may continue beyond the visible part of it, not just at its edge. Scientists say the answer depends largely on the shape of the universe. Theoretically, there are three main options, each of which is characterized by the degree of curvature of the external space. In turn, curvature is related to the mass of the universe. If we take individual parts of the sky, very large objects can affect the fabric of space and the energy of its expansion. Scientists know of examples of supermassive black holes destroying everything around them. How does this affect the universe at large? The actual density of space may exceed the critical density. That is, the mass is sufficient to stop the expansion of space, and it will spread uniformly. In such a model, the universe is closed and finite, although not precisely defined. To understand this better, imagine two parallel straight lines on a wide surface. The lines will not be parallel to each other forever and will certainly intersect. An example of this is the meridians, which cross the equator at right angles and will remain parallel at that point, but at the poles they intersect. Moving in one direction, our spaceship will return to where we left off. However, in the case of the universe, a complete analogy with the Earth is still inconsistent. Let's not forget the expansion of space. Scientists see galaxies moving away. This happens when viewed from any point in space in all directions. They move at the same speed everywhere. But the farther from the observer, the faster. For example, you are looking through a telescope, of course, from our Milky Way. You see Galaxy B moving away from you at a distance of 16,000 kilometers per second. But if some hypothetical alien from Galaxy B looks through his alien telescope, he sees our galaxy flying away from A. For an alien, it travels at 16,000 kilometers per second, and vice versa. Meanwhile, an alien race from Galaxy C is located in the same direction as B, but twice as far from Earth. From point C, the alien will see Galaxy B traveling at 16,000 kilometers per second. Our distant Galaxy A is traveling at 32,000 kilometers per second. You will see that Galaxy C is accelerating at a similar speed, 32,000 kilometers per second. So everyone will have a different point that produces the same results. Thus, a spherical universe can probably be compared to a helium balloon inflating and expanding in all directions. On the larger scales of the universe, the process is faster than the speed of light. According to this model, we will never be able to fly through space, complete the cycle, and return to the starting point. At the same time, scientists believe that another flat shape of the universe is more promising. This is possible if the mass of the universe is approximately equal to the critical mass. Then its expansion slows down to infinity. Einstein called this model an infinite but not bounded universe. A flat universe is consistent with observation and theory, so this idea is at the heart of modern cosmology. A time when data from orbital observatories were confirmed to study relic radiation. They showed that space is completely non-linear. The universe is as flat as a large sheet of paper, at least within the limits of astronomical measurements. So, in a new study, an international team of scientists shows that relic radiation has caused significant temperature changes over billions of years. Astrophysicists calculated the predicted amount of change and compared it with what they actually observed. If the data is inconsistent, the parallel lines of light rays have changed direction over time. Then the universe would bend its shape. In the end, they found small inconsistencies in the models, namely small shifts in the relic rays. The culprits are probably supermassive voids, where the density of galaxies is thousands of times less than the average of the universe. In contrast, superclusters such as the Big Dipper and a Shepley are so packed with celestial bodies that other galaxies begin to orbit them. To us, such things seem endless. However, they are very small in spatial scale. In large regions, for example, 200 million light-years away, the matter in the universe remains homogeneous in all respects. The situation is similar with the curved area. According to American astrophysicist David Spergel, the universe has flattened out due to rapid expansion. We know that in the beginning the universe was a ball of energy exploding at incredible speeds over vast distances. This process resulted in the area being flat, or very close to it. We can fly around the flat, expand the universe as we please, and everything around us will not change. We will not reach the edge. We are going to find more galaxies, stars, galaxies, and black holes. Endless. Meanwhile, monitoring the relic's radiation revealed some strange, unexplained anomalies, like large structures that shouldn't be there. Then there are the inexplicable patterns in the light of the Big Bang. According to an international team of astrophysicists, all this can be explained if the universe is like a simple donut. A recent study revealed that the unusual nature of the relic radiation in March 2023 is due to the complex shape of the universe. It's flat, but it doesn't look like a piece of paper. Airplanes are different. For example, if you draw parallel lines on a piece of paper and then rotate it, you get a cylinder. All the lines there would remain parallel. The cylinder will remain geometrically flat. Only its spatial characteristics will change. If you join the edges of this cylinder together, you get a shape like a donut. Or here is another version of the complex flat form. Take a thin strip of paper, turn one part of the strip 180 degrees and connect its edges. As a result, you will get a Mobius strip. This object is also geometrically flat because parallel lines do not intersect. In total, there are 18 geometric flat three-dimensional objects with different spatial shapes. A more complex universe than a simple flat one could explain the anomalies in the relic radiation. To do this, scientists say, it needs to be like a donut, not a stomach. If we travel through such a circular space, we will have a fantastic experience. Far away, scientists believe, we can see a copy of ourselves, much younger. For example, let's take a universe theorized to be 1 billion light-years in diameter. In this case, astronomers will observe the Milky Way galaxy as it was 1 billion years ago, then another copy created 2 billion years ago, and so on. And the copy may be deliberately reversed. But if the density of the universe is too low, there will be no spheres, no planes, no donuts. Then, the weight of matter will no longer be able to hold back the expansion of space, and the universe will bend into a saddle shape. But is such a scenario even possible? The curved shape contradicts an accepted principle in cosmology that the universe grew to enormous size moments after the Big Bang. At the same time, observations of the WMAP microwave zone provide a basis for viewing a version of the curved space. They showed that hot and cold spots on one side of space are at higher or lower temperatures than the other. That is, the universe may indeed be saddle-shaped. Planck satellite data recently confirmed this hypothesis. What does a boy-shaped universe look like to scientists? There, any object that appears to be moving parallel to another object is actually moving away from it. Therefore, light rays travel in curved paths. In particular, they follow the lines that make up the shortest distance in the curve width. This is how airplanes follow great circles as they fly around the Earth. Astrophysicists say that the universe was bent by some catastrophic impact or other major catastrophe. For example, our universe could collide with another universe, but this theory is now considered by most cosmologists to be less plausible than the earlier theory. So, can we finally settle on a flat universe? Indeed, the WMAP microwave anisotropic zone recently made new measurements of the microwave background variations. The apparatus tried to determine whether the universe was open or closed. The result is flat. The error is only 0.4%, which is definitely very small, but they leave doubt. How to distribute them? In the near future, astronomers will not be able to see our universe beyond the metagalaxy. However, scientists are trying to do this with theoretical calculations and modeling. For example, the Standard Model of Physics helped predict many particles, in particular the Higgs boson, long before its discovery. Physicists thought that such particles existed, and this helped to discover the breast. In time, the theoretical study of the universe may also yield results. Other than that, it's absolutely fantastic. Now, imagine a version where outside the universe there is no time and no space, where the usual physical laws stop working. And concepts such as matter, and energy did not exist at all. A logical extension of this was the hypothesis that our universe is part of some mega-scale cosmic structure. It is probably located in multidimensional space, and our universe, which appears to be very large, actually appears small, even partially reflected in this structure. The idea of a multiverse resonates closely with this theory, which is similar to a multiverse bubble. They are separated by thin sections that cannot be overcome. Or maybe, but only under certain conditions. According to this hypothesis, our universe began as a bridge within a larger parent meta-universe. Its birth may involve changes in the bridge wall, which have been identified as large-scale perturbations of space. One of the results may be an anomaly in the cosmic microwave background seen by the WMAP and Plan C observatories. Thus, there are several universes, and each of them is a separate place with its own physical laws. Perhaps there are strange forces and principles at work there. If we reach them, we can never understand them. Or, alternatively, it can be very simple to do. Of course, the scale of the universe is amazing. Its edge is like an unimaginable distance, and it may not happen at all. Therefore, it is not yet known whether there will be an end to our space travel. However, we will continue to reach the edge of the universe using the new theoretical calculations and observations of scientists. Thus, a unique EMI research center was established in South Korea, which will study the secrets of the universe. It is located at a depth of 1,100 meters under Mount EMI. The area of the center is 3,000 square meters, where more than 10 experiments can be conducted simultaneously. An underground facility will allow researchers to detect signatures of specific materials, objects, or structures. In this case, the underground will not interfere with background noise or external radiation. In addition, scientists hope to study the microwave background anomaly using ground-based telescopes. Any discrepancy in the expected parameters can provide valuable information about the shape of the entire universe and its edge presence. Step by step, we continue to move towards the limits of the universe. That means even more amazing space adventures lie ahead.